Today's unusual question is a little bit weird. When two persons come closer, do they attract each other? Do they have any gravitational pull? Can it be applied between these two persons? The funny answer is yes. Every object with mass exerts a gravitational pull or gravitational force on every other object with mass. That is the law of gravitational pull. So technically, two people do exert a gravitational pull on each other. However, this force is incredibly weak, especially when you compare it to the gravitational force exerted by Earth or the gravitational force exerted on Earth by Sun, kind of things. The reason for this is that the masses of people are relatively small, very small, compared to Earth or Sun. And the gravitational force is directly proportional to the product of the masses. That means when mass increases, gravitational force will increase at the same time. Additionally, the distance, that also matters, because the distance between two people is typically very small, which further reduces the gravitational force between them. While the force exists, it's so minuscule, so small, so tiny that we don't perceive it in our daily lives. Other forces, like electromagnetic forces, are much stronger and dominate our interactions, that we will discuss in our future video. But since we have started with two persons, very relatively small two masses, let us try to understand that difference between gravitational pull, gravitational force, and whether the gravitational pull, we usually know that dark matter has a very strong gravitational pull than our perceived matters that we see or feel or kind of things. Now, whether there is a difference between the gravitational pull exerted by the dark matter and our Earth, suppose, and there is, at least till today, there is no direct evidence that will claim or that will say that there is a difference. Basically, there is no difference. Fundamentally, there is no difference between the gravitational pull exerted by dark matter and the Earth. Both exert gravitational force according to the same laws of physics. Basically, it's a gravitational force. Specifically, there are two laws that govern it. Number one is Newton's law of universal gravitation and Einstein's theory of general relativity. Now, how these laws interact with each other or depend on each other, etc., I will talk in a future video, definitely. But let us break it down first. What is Newton's universal gravitation, law of universal gravitation? This law states that every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This law applies to both dark matter and ordinary matter, like the Earth. On the other hand, Einstein's theory of general relativity explains gravity as a curvature of space-time caused by mass and energy. Both dark matter and ordinary matter contribute to this curvature, leading to gravitational attraction. However, there is one key difference. What is the difference? The difference that makes is density. Density makes the difference, because dark matter is far less dense than ordinary matter. While Earth is a compact object with a relatively high density, dark matter is distributed more diffusely throughout the universe. This means that the gravitational pull we experience from dark matter, even though it's more abundant, is generally weaker compared to the Earth's pull. So we can conclude that both dark matter and the Earth exert gravitational force following the same physical laws. The main difference lies in their density and distribution, which affects the strength of their gravitational influence on us. Now, naturally, another question comes to our mind. Is there any relation between density and gravitational pull? Because we see that there is a relationship between density and gravitational pull. Especially when you consider mass and gravity. The primary factor that determines gravitational pull is mass. Remember, the primary factor that governs or that determines the gravitational pull is mass. More mass means a more gravitational pull or stronger gravitational pull. Now, density and mass. Density is mass, practically unit volume, mass unit volume. So therefore, a denser object packs more mass into a smaller volume. That's it. That is why gravitational pull and density has a relationship. For objects of the same size, a denser object, more dense an object is, will have a stronger gravitational pull due to its greater mass. Now, another factor is also important, that is distance. Gravitational pull decreases with distance. That means if distance increases, gravitational pull decreases. So even if an object is denser, however denser it is, if it is in a very distant, say it's in a distant galaxy, okay, its gravitational pull will be weaker if you are further away from it. We can give an example also. Consider two spheres of the same size, one made of lead or lead, whatever you say, lead, dense lead, and the other made of styrofoam, okay, that which is a foamy object, okay, suppose a bubble kind of things. It's less dense, of course. So even though they are of the same size, the lead, that means anything, consider iron, say, instead of lead, consider iron. Even though they are of the same size, the iron sphere will have a stronger gravitational pull because it contains more mass. And the bubble, foamy bubble, although it is of the same size, but it contains less mass, so therefore it has practically no gravitational pull. Now, we know that gravitation, that means the gravitational constant G, capital G, it's a constant, right? Then, but we see that gravitational pull changes with mass, with distance, etc., etc. Then, how can we say that gravitational pull is a constant or not? Now, look, you need to understand this topic in a different way, because gravitational constant or capital G is a constant, indeed a constant. That means it does not change. But the gravitational pull experienced by an object can vary depending on other factors. What are the other factors? Number one factor is mass. Again, I repeat, G is a constant, but mass can vary. One object has more mass, one object has less mass. Second factor is distance, because distance between objects, as it increases the pull, it directly affects the gravitational pull, and gravitational pull decreases. So G remains constant, but these factors, that means these variables, rather I would say, like I said, they directly change the value. They keep changing the value. Another thing is distribution of mass. The way mass is distributed within an object can also affect its gravitational pull. For instance, a hollow sphere might have a different gravitational pull on its surface compared to a solid sphere of the same mass and radius, right? Like our Earth. So while the fundamental constant G, capital G, remains the same, the overall gravitational pull experienced by an object can change based on these factors. Now remember, between two persons, this G, capital G, constant, remain the same. but there are a lot of other factors: mass, distance, hollowness, density, etc., etc., etc. They basically make the gravitational pull weaker. So gravitational pull is itself is not a constant, but the underlying constant capital G that governs this force is indeed a constant throughout the universe. Between two people, between two persons, between sun and earth, between imagine any galaxy or anything, it remains the same. Gravitational force remains the same. In our previous video, we have discussed how two people do exert a gravitational pull on each other. However, we also discussed that this force is incredibly weak, especially when compared to the gravitational force exerted by Earth. Just because it is true that every object with mass exerts a gravitational force on every other object with mass, but the amount of mass, if it differs, I mean, if it's small, then the pull is incredibly weak, and if the mass is big like Earth, the pull is massive. So at the same time, we also talked about the electromagnetic forces, which are much stronger and dominate our interactions. But in today's video, we will be going to find out how electromagnetic forces dominate our interactions in several ways. Number one is chemical bonds. Atoms are held together by electromagnetic forces between their positively charged nuclei and negatively charged electrons. These factors are responsible for the formation of molecules, which in turn make up everything around us, including our bodies. Number two is friction. When two surfaces come into contact, the electromagnetic forces between the atoms of the two surfaces resist their relative motion. This resistance is what we call friction, which plays a crucial role in many everyday activities, from walking to driving, everything. Number three is light and heat. Electromagnetic radiation, such as visible light and infrared radiation, is a form of electromagnetic energy. This energy is constantly being emitted and absorbed by objects, influencing their temperature and appearance at the same time. Number four, and the final one, is electricity and magnetism. Electricity and magnetism are two sides of the same coin. Why? Electric currents generate magnetic fields, and charging magnetic fields induce electric currents. This principle is used in countless technologies, from electric motors to generators. While the electromagnetic force between two individual people is not directly noticeable, it is the underlying force that governs the interactions between the atoms and molecules that make up their bodies. For instance, when two people touch, the electromagnetic forces between their skin cells prevent their bodies from passing through each other. I again repeat, when two people touch, the electromagnetic forces between their skin cells prevent their bodies from passing through each other. So while gravity is a fundamental force that shapes the universe on a large scale, of course, electromagnetic forces are the dominant forces that govern our everyday experiences and interactions. Capital G. Thanks for watching. See you in the next video. Till then, goodbye. Stay safe and take care.